what I want you to be able to do is I want you to read a problem that is given and explain what is the problem with your own words. Go ahead.
Okay, so the problem here is trying to figure out the maximum number of cars that can flow from the west point to the east point. So that's from 1 to 6. What's the maximum number of cars that can flow from there to there? And you can figure that out by this being a one-way, this being a two-way, this being a two-way, and you could easily calculate it out to see.
Anything else that is there that you didn't say?
I don't know. Help me out.
Okay. Look at what is there. These numbers here are the hundreds of cars that can go for each particular flow. So from node 1 to node 2 on this flow, we can have 300 cars. From node 2 to node 1, we can have 100 cars. As a result, what I want you to know is how each one of these nodes is connected directly, not indirectly, directly to the other nodes that is connected. That means that node 1 is connected directly to which flows? Down a little. Down a little.
Node 1 is directly connected
to which flows? Which nodes?
2, 4, and 3.
And anything else?
And 6.
Correct.
Oh, I didn't see that.
4 is connected to which nodes?
1, 2, 3, all of them. 1, 2, 3, 4, 5, and 6.
No, not all of them.
No, not 5.
Not 5.
Because there's nothing connected up there.
So, therefore, there are two things that are important. One is, how are the connectors between nodes? 2, what is the maximum amount of flow that we can have in every connection? And what we want to do is we want to find out what's the maximum amount of cars that they can depart from here through the system, go all the way to point 6, and then be able to come back. And we want to see how this is going on. What we do not want to have is we do not want anything to go to 3, 4, 2, 5, and be stuck there. That means that everything that gets into every node needs to get out of every node. As a result, we need to pay attention to each one of the nodes we have. How many nodes do we have?
6.
Good. Therefore, we need to write an equation for each one of the nodes. In the equation, we need to have what gets into the node and what gets out of the node. If we don't want anything to stay in 3, everything that gets in needs to be equal to everything that gets out. How do we write mathematically when things are getting out? Positive or negative?
Negative.
When things are getting out,
Negative.
I have a pencil, I give it to you. Take it. Do I have a pencil?
No, it's negative.
What happened to the pencil?
It went away.
We transferred.
She has the pencil. I don't have the pencil. She has the pencil. Minus a pencil for me, plus a pencil for her. I get it back. Minus a pencil for her, plus a pencil for me. Clear?
Yeah.
That means for node 4, I want each one of you and Denali to find out how many cars they get in and how many cars they get out of that particular node. Can you do it?
Yeah.
Okay, what you have to see is from where node 4 receives cars.
So there's only...
Here's the graph. Go on and tell us. Nada. Here. Here.
I heard a
Node 4 gets cars from where?
from 6 to 1 and 3.
6, 2,
1.
1, and 3.
And they
Node
go
4, sends cars 2.
2, 6, and 3.
No.
Good.
Yeah.
2,
Yeah.
6,
Oh, yeah.
and 3. What we have to do is these things to be balanced correctly. This is what we have to write in mathematical terms and solve it. Now go to your Mathematica file and we can see what we have there. In the Mathematica file, what do we have? I want to maximize the flows that they can return from 6 to 1. Is this clear?
Yes.
I want to maximize everything that can return from 6 back to 1. As I want to maximize everything that would return from 6 to 1, what I have to do, I have to take into account what happens into each one of the nodes. I have 6 nodes. From 6 I go to 1, and from 2 I go to 1. This is the input or the output in node 1. And from 1, the outcome is from 1 I can go to 2, from 1 I can go to 3, and from 1 I can go to 4. So what gets into 1 minus of what gets out of 1 is 0. That means nothing stays in 1. And I don't want you to do it the way that the book has it, because the book does not put these things in parentheses and does not group them, puts them all together. And if you have them all together, you may get lost. But the best way not to get lost is to group them all together. Positive, what
Which
is
file
getting...
was that one? Which file was that one?
Same file.
Yeah. But it's using the parentheses.
It's using the
Yeah,
parentheses.
it's
Good.
143.
So the second edition then that I used to make copies is using the parentheses. The first didn't have it. So these 3 lines, these 3 equations specify the balancing of the flow in each one of the nodes. Mary Lou, is that clear? Yes or no? Okay, can we repeat it then? What is the meaning of this equation here? See, Holly can't hear you. I want you to tell me in plain English what is the meaning of these 6 equations. Loud enough so Holly and Jennifer and Jessica can hear you.
2 goes to 6, and 4 goes to 6, and 5 goes to 6.
Good.
And that one, and then that one is 6 goes to 1, 6 goes to 2, and 6 goes to 3.
Correct. This is what gets in the 6, and this is what gets out of 6. What gets in the 6 must be equal to what I get out of the 6. Another way to do that in a mathematical term, if you want not to have it equals to 0, you can have the equality at that particular point, which is an equivalent statement. If you have whatever it gets in equal to whatever you get out, is the same thing that if you have whatever gets in minus to whatever gets out is equal to 0. Different people in different books, they have it in different terms. One way or the other doesn't make any difference. This is the way that we can say it. That takes care what's happening to the node. That takes care of what we have here in your nodes. Are the restrictions that they tell me what happens in this node, this node, this node, this node, this node, and this node. Then I have to take into consideration what is happening in the flows, in the arcs. And I want to make clear that from this point to this point, I can have 300 cars move one direction, but only 100 cars move the opposite direction. And from this point to this point, only 200 cars can go. And from this point to this point, 1,000 cars can go. That means that now I need, not for the node, but for the flow, for the arc, to have a specification of what's happening in each one of the arcs. And what I want to do is I want to go and translate the graphical information to mathematical information. That means from 1 I can go to 2, and the maximum amount is 300. From 1 I can go to 3, and the maximum amount is 1,000. From 1 I can go to 2, and the maximum amount is 200. I'll go through all the flows. I need to be very careful, so I would count how many of these restrictions I have. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I need to go back to the graph, and I want to see, do I have 16 flows? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then I'm correct. But I need to have one statement for each one of the flows that specify how much I will go from one place to the other. Go back to Mathematica, and I have another solution. And the other solution is all these flows can have a value that is positive. That means 0 or more than 0. If the value is 0, that means nothing is passing from that particular road. If it's more than 0, can be up to the upper limit that I have here. And if I have all that stuff with the definition of how many variables, how many flows I have, I can solve it. And as I can solve it, I can get a solution. How many cars I can have going from point 1 to point 6, the maximum amount of cars. Anastasia? 500. And if the maximum amount of cars is 500, then the cars would get out of point 1 need to be how many? Anastasia, from point 1, how many cars they get out? 500. That means 200 they go to point 2, 200 they go to point 3, and 100 they go to point 4. From point 2 now, how many cars they move? From point 2. From 1 to point 2, we have 200 cars. That means 200 cars need to get out of point 2. And out of point 2, 200 cars go to point 6. From point 3, what is happening to point 3? 200 cars went to point 1. Therefore, these 200 cars that they want from 1 to 3, from 3 they can go to 5. And now 200 cars are in point 5. How many cars I have in point 4? 100. They came from 1. Therefore, from point 4, 100 cars go to point 6. Clear? And I have in 0.5 200 cars. What happened to these? Do they go to 3 or do they go to 6? So from 5, 200 cars, they go to 0.6. And from 6, 500 cars go to 0.1. They return back. The maximum amount of cars that I have are 500 that for this network they move in. The book stops here, you give this answer, and you're fine for the book. Now, you're not fine with me. What I want you then to calculate is, if this is the flow that you have, and this is the capacity that you have in the roads, I want to find out how much of that capacity you utilized. Because I will explain it right now. Because from point 1 to point 3, you have capacity of 1,000 cars. But you ship only 500. That is, that road is utilized 50%. And I want you to tell me in percentages what is the utilization of all the roads. I don't know. You took 210 for that. If the road can allow you to drive 1,000 cars, and what you do is you can only have to go 500 cars. So how do you find that 50%? This is what I want you to be able to do. If you have that case, what kind of a decision you have to make? Are you going to make any decision that controls the whole situation? What kind of decisions did you make in that case? Wow. Emergency. So, this is the network we have before the computer gives me a decision. Now, the computer gives me another outcome. I know not how much each of the roads would take, but I know how much it's the actual flow of the road. Do I need to make any decision because of that? Let's see what's happening. There is a bridge here in New York that takes a lot of traffic, and there are not that many alternative. Amanda. So, there is a bridge here in New York that takes a lot of traffic, but that particular area does not have alternative ways for that particular traffic. It's the Tappan Zee Bridge. The Tappan Zee Bridge is up in the north, and it's one of the bridges that has a lot of traffic coming into the city in the morning and a lot of traffic getting out of the city in the afternoon. As a result, in that particular bridge, they remove, based upon how much traffic they have and what time, the separation of the bridge in such a way they can allow more people to get in the city in the morning and more people to get out in the city in the afternoon. This is the type of a real case scenario we have to deal here. That means if I have only 50% utilization of here, how much utilization I have in this flow here from 1 to 4? From 1 to 4. What is the solution that I get?
100.
From 1 to 4, I have 100. And from 1 to 2, I have 200, 200, and 100. So this is Yeah. Then we go on and we look at the case that we have here.
Professor,
Yes.
can you go back to the mathematical thing and one second? I have a question. Why from 5 to 6 in the there you have
Hold on a
200?
minute.
From 5 to 6, why
So
do you
it's
have
not too good, right?
from 5 to 6, why do you have 200 when here in the graph they show that it's 600?
From 5 to 6.
Yes. Why not 600? Because that's what they show.
From 5 to 6, 200, right?
Are they saying 200?
Why do we have here 200? How many did we get into 5? So from 3 to 5, we have 200. From 5 to 6, we have 200. Why do we have from 3 to 5, 200? Because from 1, 200 can go into 3.
So 600 is the capacity, not
Exactly. That means, do I utilize all the capacity or not? And what I'm interested in business is to find out how much of whatever is there is not utilized. The people that write the book, and that are not in business but they are mathematicians, they want to have the right solution. But I want you to be businesswomen and businessmen, and the right solution is not good enough to have that solution, but you have to be able to tell me is how this solution is related to that particular case that you have here. Is this clear? And I want you to study that and be able to reproduce it, because I want to use that example as a model for the final exam. So that's going to be one of your problems that you are going to have. Clear? The next problem that we have here in the book problem we have in the book, you want to make another file here, is something that the technology that we use now